Okay, today we are still looking at differentiation, but we are looking at a new rule called the product rule. The product rule, it's fairly simple. You guys are going to grasp this really easy. The main thing is when to know when to use the product rule. So we use the product rule when our function y is a combination of two other functions multiplied together. For example, if we have a look down here, if this is our function here, x times x minus 10 to the power of 4, one of those function parts is x and the other one is x minus 10 to the 4. We don't have another rule how to differentiate that, and we're going to use this rule called the function rule. This is the rule here. I'm going to highlight it in blue. This is given to you on your HSC formula sheet, so you do not need to memorize it. But what we need to do is split our function y into two parts, u and v, and we will get our derivative dy dx, and the rule tells us we will have v, we will times that by du dx, and we will add to that u, and we will times that by dv dx. So the rule is given to you on your formula sheet, so we will just write that down each time, and we'll find that quite easy to substitute into. Another way that we could write the rule is over here. Now, before we look at that, we've been writing our derivative as f dash of x, and we've also been writing it as dy dx. And just to add another one in there, we could actually write it as y dash. So I could write dy dx as y dash. My v would stay the same. I could write du dx as u dash plus u times by dv dx, which is v dash. So you can see them with little dashes like that as well occasionally. So at this point, we've got three different ways to write the first derivative. Okay, let's scroll down and have a look at our question. I've worked it out here, but I'm going to write the solution as we go over to the right a little bit. Example 29. Differentiate each function, writing the result in fully factored form, then state for what values of x the derivative is 0. So there's actually three parts to that question. We're going to do each part singularly, and then we'll have the question all done. So step one is differentiate each function. I'm just going to rewrite this over to the side. So I've just written that over here again so that we can work through this together. Okay, so the question has asked us to find dy dx. So we're going to be looking at our functions first up and see, well, how am I going to do that? There's an x inside our bracket, there's an x outside the bracket. We need to use the product rule. Okay, we can't use the chain rule, we can't differentiate normally because there's two parts to our function, and there's two x's in there. So this is our y here, and we want to find dy dx. But in doing so, we need to assign a u and a v. So our u is going to be our x, and our v is going to be the second part here. Now, people in class ask, do I need to put it in that order? Could this be a v? Could this be a u? Yes, in this rule it can be, but the rule we're going to learn next, we need to have it in a particular order. So I'm going to suggest we go alphabetically. U comes first in the alphabet. Let's take our first one as u. Let's take our second part as v. Okay, so we've got a u, we've got a v. Let's go back and look at the rule. The rule says to find dy dx, we need a u and a v, which we've got. We need a du dx and a dv dx. So if I have a look over here, I've got a u, so I can differentiate u with respect to x, and that gives me du dx, and that will give me a 1. Similarly, with the second one, I have a v, and there's an x on the other side, so if I differentiate v with respect to x, I am going to get my dv dx. So we need to think about what we did in our last lesson to differentiate this. The 4 comes down the front. Our x minus 10 is now to a power of 3, and we're also differentiating what is inside that bracket. So when we differentiate x minus 10, we're going to multiply by that, which is 1. So what I end up with is 4x minus 10 to the power of 3. So I've got a u, I've got a v, a du dx, and a dv dx. So now I can write my rule down and pop these into that rule. So look at our rule again. V du dx plus u dv dx. V du dx plus u dv dx. Let's work out our dy dx. Okay, let's substitute it in. Our first part is v. Our v is this term here. So v is x minus 10 to the 4. We are multiplying that by our du dx, which is 1. So between these two terms here is a multiplication. And we're adding to that our u which is x, and we're multiplying that by our dv dx. Our dv dx is this term down here, 4x minus 10 to the power of 3. So that's our answer, but it's not neat enough, and we're not finished yet. So let's neaten that up. I don't need this 1 here. And I am going to put the 4 and the x together to make it 4x. Okay, now that is correct, but let's go back to the question. What did it say? It said differentiate each function. Well, we've done that. We've differentiated our function, writing the result in a fully factored form. We are not in a fully factored form yet. We have a plus between our two parts of the function here, and we have like terms on either side, so we can factorize that. And what's common to both of those parts between our plus sign is an x minus 10 to the power of 3. So I'm going to factorize by pulling out an x minus 10 to the factor of 3. So if I do that, what I have left here, I've taken out 3 of those powers. I have 1 left, so I'm left with 1 lot of x minus 10. I'll just put some brackets in there for now. And on this side, I've taken out all of the x minus 10 to the 3's, and I'm left with the 4x. So what we can do now is we rewrite that first bracket down. I can simplify my second bracket. I don't need these little mini brackets around the x minus 10 because it's not doing anything, but I can add that x to that 4x to become a 5x, and the 10x goes in there. Now have a look at it. Are we fully factorized? No, we're not. That second bracket has a power of 5 that I can pull from both of those. So I'm going to pop a 5 out the front. I've written it out the front just because it's a lot nicer to pull it out the front of both, but that's fine to leave it there. And I'm going to have left an x minus 2. Okay, so have a look at that again. Am I now fully factorized? Yes, I am. Have I answered the question? Let's go and check. The question asked me. Here we are. Differentiate each function. Okay, we've done our differentiation of part A of our questions. Writing the result in a fully factored form. Yep, we've done that, but we haven't answered the third part. The third part says, then state for what values of x the derivative is 0. And let's jump back over to where we are. We're down here, our fully factored form. Which values of x is the derivative 0? Well, here's our derivative. So we want to find out where our derivative is equal to 0. So where dy dx is equal to 0. Let's set this to 0 here, this part here. So we want to find where 5, x minus 10 to the power of 3, x minus 2 is equal to 0. Okay, think back what we did in our functions topic and our quadratics topic. When we have different brackets set to 0, and we don't need to look at the 5 out there, okay? We're only looking at the parts in the brackets because the 5 is not going to help us out. We're going to set each of our brackets to 0 because we don't know which one is 0. So we're going to check them. X minus 10 to the power of 3 is equal to 0, and x minus 2 is equal to 0. I'm going to solve this one on the right first because that's really easy. That gives us x is equal to positive 2. Don't really need the positive sign in there, but you can leave that in there if you like. So x is equal to 2. And on this side, what we've got is an x minus 10 to the power of 3. So what we have actually 3 brackets of x minus 10. X minus 10 is happening 3 times. I'm going to write it down once. And what we've got is x is equal to 10. When x is equal to 10, and x is equal to 10. So we have it happening 3 times. And we've also got x is equal to 2. So we've kind of got a triple root there, and we've got a single one there. So those are our solutions. And I will highlight those in blue for us. So x equals 10 and x equals 2 is where our derivative is equal to 0. Let's now go and look at the second question to have another go at it. We've got x squared, 3x plus 2 to the power of 3. We want to do exactly the same things. We want to differentiate, write in a fully factored form, and state for what values of x the derivative is equal to 0. So I'm just going to write this over to the side so we can work through it together. Okay, I've written this second function up. That is our y. We have been asked to find dy dx. Okay, it's not a straightforward one. We're going to look at our function or our y, and we're going to see that there are 2 lots of x's in there. There's an x out the front here, there's an x inside here. So we can't use a chain rule, we can't use straightforward differentiation. We need to use the product rule. So we need a u and we need a v. Our u is going to be our x squared. It's our first term there. Our v is going to be the rest of it that's left in there. 3x plus 2 to the power of 3. Now, if you ever got stuck, I guess you could expand this out. It is a cubic, and you could then expand it by x squared to get one long function. That would be a lot of work and with a lot of room for error. So doing it this way as the product rule is your safest bet to answer these questions. Okay, so if we think about what our product rule tells us, to get dy dx, we need a v du dx plus a u dv dx. We've got our v and our u. We need our du dx and our dv dx. So our du dx we find from our u function. I differentiate u with respect to x and I end up with 2x. My second part here, v, I can get my dv dx from there, and I'm going to differentiate this part. Remembering, there's a little extra trick in this one. The 3 comes down the front. We still have a 3x plus 2 to the power of 2, and we're going to multiply by the differentiation of what is inside those brackets, which is 3. So what I end up with is 9, 3x plus 2 to the power of 2. Let's import all those into our formula. So dy dx is going to be equal to, sorry, I'm zooming in and out here, v, which is that part in here, 3x plus 2 to the power of 3, times du dx, which is 2x, plus u, which is x squared, times by dv dx, which is over here. And our dv dx, it's a big long one, 9 lots of 3x plus 2 to the power of 2. Okay, we need to remember all our algebra rules, but before we do anything, let's neaten it up. So our dy dx is equal to, I'm going to bring the 2x out the front of this bracket. Just be careful that when you're doing this, you're setting it out really neatly. This was our y, this is dy dx. A lot of people are popping y equals and then going equals for their dy dx. You need to be specific, and we need to make sure that we're noting that what we're doing here is dy dx. Otherwise, you might lose some marks. Okay, 2x is out the front, so that looks a little bit neater. Plus, I'm just going to pop the 9 out the front of the x squared because it looks a bit neater that way. Get rid of the times sign, and we're writing it like that. Okay, now that is correct. That is our answer, but it wanted it in a fully factored form. So what we are going to do is see what is common to both of those brackets. I can note that there is an x that is common to both of them, so I'm going to factor out an x. But I'm also going to factor out a 3x plus 2 to the power of 2. So that's our biggest part that can also go in. Okay, there we are. That's what's common to both. That's what I'm factorising by. What have I got left? If this is what I'm factorising out of this term here, I've got left a 2 and a 3x plus 2. Plus, over here, I've taken out an x. I'm going to have a 9x left. And I've taken the whole of the 3x plus 2 all squared out. Okay, we're nearly there. Write that first part down again. And what I'm going to do is I'm going to multiply through by those. 3 2s is 6x plus 4. That 9x just tacked on to the end. One more step to tidy it up, and you may have done that in one step if you're quite good with that. The 9x and the 6x gives us 15x plus 4. That is our fully factored form. If you have a look, there's nothing common that I could take out of anything else there to help us out. The third part was finding when our derivative was equal to 0. So we wanted to find when dy dx was equal to 0. So let's set this part, which is our dy dx, equal to 0. Okay, again, thinking back what we did when we looked at our functions and our quadratics, when we had different parts in brackets equal to 0, we didn't know which part was the 0. One of them is, but we set them all to 0. So our x must be equal to 0 here. Our 3x plus 2 squared is going to be equal to 0. I'm just going to write 1 in there. It's going to be a double root for that one. And we've got 15x plus 4 is also equal to 0. So we've got our first solution there, which is x equals 0. We have our second one here. 3x plus 2 equals 0. If we quickly rearrange that, we're going to get x is equal to minus 2/3. Okay, if you need to pause it and double check that you're happy with that, do that. And lucky last, we're going to have x is going to be equal to minus 4 over 15. Those last two don't break down into any simplified form, so those are our solutions. Now, I always want to go back and check, have I answered the question? And I want you to do that as well. Let's go back, read that question. Have we done exactly what it's asked us to do? Sorry, my screen's gone blank there. Yes, we've differentiated, we've written it in a fully factored form, and we've found the values of x for which the derivative is equal to 0. Excellent. Have a go at the examples yourself and work through exercise 8H.